Okay, I'm going to start with the recording. So previously we have learned how to calculate the various vector product or differential vector product, differential integration for the Cartesian coordinate and cylindrical coordinate and spherical coordinate. And today we will be thinking about more general curvilinear coordinate. So this coordinate is a general coordinate with the three mutually perpendicular axes. We have three mutually perpendicular axis. So let's have somewhere in the center as origin. So we have some coordinate which will be denoted by Q1, Q2, Q3. So Cartesian coordinate will be denoted as, for Cartesian coordinate, Q1 is simply X, Q2 is Y, Q3 is Z. Cylindrical coordinate Q1 is rho, Q2 is phi, Q3 is Z. And spherical coordinate right? Q1 is R, Q2 is theta, Q3 is phi. Okay. Let me just turn off the recording, okay? So that's the original position that I wanted to have this new coordinate, Q1, Q2, Q3, and two surfaces meeting perpendicular axis define the axis. So let's say we have this surface. This is Q1 is constant. This is surface perpendicular to Q1, and we have another surface. Let's say, what is this? Oh no. So this is a surface. Q2 is constant, and we have yellow one. This is surface. Q3 is constant. So Q1 axis can be defined by two surfaces, which is one is Q2 is constant, another one is Q3 is constant, right? And likewise, this Q3 surface axis can be defined by two surfaces which are meeting perpendicular to each other. One is Q2 is constant, another one is Q1 is constant. It's either way. So any two perpendicular surfaces define the axis. So two surfaces meeting or intersecting perpendicular to each other. Defines the axis, an axis. So for example, surfaces Q3 is constant, Q3 is constant, and Q2 is constant. Defines Q1 axis. That's one example. So assuming that we have two different points, one is P, which is Q1, Q2, Q3, another Q1 plus DQ1, Q2 plus DQ2, Q3 plus DQ3. So distance between P and Q. You can ask, how do we define two different points in curvilinear coordinate? So let's simplify by considering the one-dimensional case. So case 1, if the distance between Q1, Q2, Q3, and Q1 plus DQ1, Q2, Q3. And we have considered the case for the cylinder that if the radius is r and this is phi, this distance is approximately rho delta theta, right? Not delta theta. So if the coordinate is non-Cartesian, the distance is a little bit more complicated. So let's denote this distance as dl1, and I'm going to simplify some factors, scaling factors, dq1. The simplest case for h1 is 1. This h1 is a scaling factor for the distance, or you can sometimes define as a metric. Oh, you need time to copy? I usually like blue colors, so I'm mostly writing blue, but I'd like to ask a question if you can read it clearly. Blue is okay? So another page. Choose a template. So likewise, we can define dl2 as a distance between Q1, Q2, Q3, and Q1, Q2 plus DQ2, Q3. So dl2 is in general H2, Q1, Q2, Q3, DQ2. And dl3 is distance between Q1, Q2, Q3, and Q1, Q2, Q3 plus TQ3. And I'm going to define as H3, Q1, Q2, Q3, TQ3. So in principle, I'm assuming that the metric tensor is diagonal. So we summarize DL1, H1, Q1, Q2, Q3, TQ1, DL2, H2, Q1, Q2, Q3, TQ2, DL3, Q1, Q2, Q3, TQ3. So for example, Cartesian coordinate H1, H2, H3 are all 1, right? And Cartesian coordinate, the distance between the two different points is just dx, dy, dz. So in this case, H1, H2, H3 are all equal to 1. On the other hand, the cylindrical coordinate is rho phi z. So H1 is actually H1 is 1, H2 is rho, H3 is 1. Spherical coordinate coordinate is defined by r theta phi, right? Rho phi z. So H1 is simply 1, H2 is r, H3 is r sine theta. And I derived why this is so in last class, right? So I have the distance between the cylinder and spherical coordinate. So you can just stabilize here is 1. So can I move on to next page? So assuming that we have Q1, Q2, and Q3, and we have some surface, let's have Q1, Q2, Q3 are constant. And the gradient is defined as a maximum change of function along the direction. So the gradient of f is actually delta r over delta f. So it can be checked as dl1 over df, dl2 over df, dl3 over df can be written as following: h1 partial q1 partial f1 f q2 h2 partial q2 partial f q3 h3 partial q3 partial f. So q1, q2, q3 are unit vectors along the q1, q2, q3 direction. So q1 hat, q2 hat, q3 hat are unit vectors along q1, Q2, Q3 axis respectively. So I can write down the gradient in 3 different coordinates as simply in Cartesian coordinate, and so far there are 19 different curvilinear coordinates known to us, and I guess we are lucky because we have invested only 3. But there are other 16 different coordinate systems which can be very complicated. So gradient of f is simply x partial f, y partial f, z partial f. Cylindrical coordinate stop recording. Gradient f is rho partial f, phi rho partial f, z partial f. And spherical coordinate gradient f is r partial f, theta r partial f, phi r sine theta partial phi partial f. So gradient is easy, and we still need to find the formula for the curl and divergence. So curl is related to the closed line integral, right? So give you some time to copy. So can I on to next page? And just in case, let me just save it. Click save. I thought it was recording, but how long I was doing with the off the record? I don't know. Okay, so I'm going to repeat it again. So we are going to consider this closed line integral in Q1 and Q2 surface, starting from A, B, C, D, A again. So center point will be defined as Q1, Q2, Q3, and so we are going to 1, 2, 3, 4. So this point will be Q1, Q2 minus delta Q2 over 2, Q3, and this point will be Q1, Q2 plus delta Q2 over 2, Q3. Let's start with 1 and 3. And this distance is dl1. So A to B and function f will be defined as Q1 f Q1, Q2 f Q2, Q3 f Q3. So f dl along this line 1, So this direction is the Q1 direction, right? So the F dot dl is simply A to B FQ1 dl1, and it can be using mean value theorem. We can calculate FQ1 evaluated Q1 Q2 minus delta Q2 over 2 Q3 times H1. But you have to remember that H1 is also a function of Q1, Q2, Q3. So Q1, Q2 minus delta Q2 over 2 Q3 and delta Q1. It's too long, right? So let me introduce simplified notation that says FQ1 H1 just evaluated at this point. Q1 Q2 minus delta Q2 over 2 Q3 delta Q1. On the other hand, 3, that's 1. 3 is C to D F dl. But on this 3, the direction is in the opposite of 1, right? So direction is minus Q1 direction. So that will be minus of C to D F Q1 dl1, and maybe we need some boundary for that. That is using FQ1 minus H1 evaluated at Q1 Q2 plus delta Q2 over 2 Q3 and delta Q1. I'm tempted to make a copy of this, and if just for the record, let me take the record of it again. Maybe each time I have to draw it again. That's not very convenient. So now, because I cannot make a copy and paste, I have to memorize. 1 and 2 is 1 is evaluate at Q2 minus this, and 3 is we have minus sign, but evaluate that there is plus. So new page, 2 slides back. So we still need to do this 2 and 4. So let's all remember 1 plus 3. 1 plus 3 will be F Q1 H1 evaluated at Q1 Q2 minus delta Q2 over 2 Q3 minus F Q1 H1 evaluated at Q1 Q2 plus delta Q2 over 2 Q3, and we have a delta Q1. And we have something complicated. I told you do nothing, right? So do nothing means sometimes you multiply by 1 or you can add 0. In this case, let's try to multiply by 1. So we can actually make delta Q2, right? And divide by delta Q2. And also multiply by H1 and H2. and here H1 and H2. And let me see, Q1, Q2, this is Q3, so this is H1 dl1 delta Q1, H2 dQ2. So this is actually area, right? So this can be area, normal to Q3 axis. So let's call this area as ds3. Then everything is, you can put, this is simply minus, so partial H1, H2, partial Q2, partial FU1, H1, evaluate that Q1, Q2, Q3 with H1, H2, delta Q1, delta Q2. So using mean value theorem again, it can be integrated back into this. H1, H2, partial Q2, partial FQ1, H1, ds3. And we are going to get why I denoted the surface area as ds3. And we still need to do Q2 and 4, right? So let me just go back, do it here again. Q1, Q2, Q3. So now this is 2 and 4. Center is again Q1, Q2, Q3. It looks like I have to draw it every time with this little bit dumb app. So the center point, so this is going up and this is going down. So this is DL2. And this point is Q1 plus delta Q1 over 2, Q2, Q3. And this point is Q1 minus delta Q1 over 2, Q2, Q3. So if I do this integral, two plus 4 will be the following, because for the 2, direction is in Q2 axis, right? So we are going, the inner product will give you FQ2. And this is minus. So 2 to plus will be something like this. FQ2, H2, evaluated at Q1 plus delta Q1 over 2, Q2, Q3, minus FQ2, H2, evaluated at Q1 minus delta Q1 over 2, Q2, Q3, with the delta Q2. And we do the same step. Divide by something, multiply by something, and then change it back into the mean value theorem. Then you just fill the 2 lines as a homework. We have H1, H2, partial Q1, partial FQ1, Q2, Q2, H2, ds3. So you fill this step as homework. one thing looks better is it looks more colorful. So can I move on to next page, or you still need time to copy? Next page. Three. So result compare with the Q1, Q2 minus, right? So I keep drawing this. Let me see. In this case, we have the following. Oops. That's Q3 partial, Q1 partial, H1 1 over H1, H2 partial, Q1 partial, FQ2, H2 minus partial Q2 partial, FQ1, H1, DS3. So this is basically curl of F over Q1, Q3 component. Let me do. We can do the same thing. If we do this Q1, Q3 surface, what do we get? Or Q2, Q3 surface. If we do this, on Q2, Q3 subplane, you can do the same analysis, right? So I will leave it as homework. Then it gives this DS1, H2, H3, partial, Q2 partial, FQ3, H3 minus partial Q3 partial, FQ2, H2, DS1. So this will be is called Q1 component, and of course this is homework. And if we do the other thing here, Q3 Q1 surface, and this surface is TQ2, DS2. Here is the following. Here it's actually this DS2, 3, 1. H3, H1, partial Q3, partial FQ1, H1 minus partial Q1 partial FQ3 H3 TS2, and of course this will be core FQ2 component. So this is also homework. So it don't take too long, maybe half an hour each. So it will be 1 hour homework. I showed for Q1, Q2 surface. So you can exactly the same thing for Q2, Q3 surface or Q3, Q1 surface. That would be easy, right? So can I move on to next page? Or still need time to copy? Nice, colorful. Green and blue. My favorite color. 8 page. So in summary, so core F, Q1, H2, H3, partial Q2, partial. Maybe I better use bracket. Where is it? This. Oh, it's okay. I have a brace here. FQ3, H3 minus partial Q3, partial FQ2, H2 plus Q2, H3, H1 partial Q3, partial FQ1, H1 minus partial Q1, partial FQ3, H1 plus Q3 that I derived, H1, H2, partial Q1, partial FQ2, H2 minus partial Q2, partial FQ1, H1. Let me just check with my previous result. So H2, H3, H3, H1, 2, 3, 1. Okay, correct. So for Cartesian coordinate, you are interested in the explicit formula for 3 different coordinates, right? So Cartesian coordinate core F H2, H3 are 1, right? So this is X partial Y partial FZ minus partial Z partial Fy plus Y partial Z partial Fx minus partial F partial Z plus Z partial X partial Fy minus partial Y partial Fx. Cylindrical coordinate call F. Q1 is rho, so rho. H2 is rho. H1 is 1, H2 is rho, H3 is 1. So remember that. So 1 over rho. Partial phi, partial Fz, minus partial Z, partial. Here you have to be careful because H2 is now rho, right? So F phi rho plus phi H3 is 1, H1 is 1, so you don't have to worry about that. So partial Z, partial simply F rho minus partial rho, partial, that's 3, right? Fc and Z. H1 is 1, H2 is rho, so 1 over rho, partial rho, partial F phi rho minus partial phi, partial F rho. A bit more complicated. And for 3, let me record. So I have to write it down again. Sorry. I tried to make a copy, but it doesn't work. So actually, it's good for you. Q1. So H2, H3, partial Q2, partial FQ3, H3. Let me just make sure that I have a correct formula. Right. Minus partial Q3, partial FQ1, FQ2, H2 plus Q2, H3, H1, partial Q3, partial FQ1, H1 minus partial Q1, partial FQ3, H1 plus Q3, H1, H2, partial Q1, partial FQ2, H2 minus partial Q2, partial FQ1, H1. Let me just double check. H2, H3, H1, H1, H2. Okay, so spherical coordinate. It's R theta phi, and H1 is 1, H2 is R, H3 is R sine theta. So curl in spherical coordinate is given by R direction. H2, H3 is 1 over R square sine theta. Partial theta, partial F phi R sine theta minus partial phi, partial F theta R, are very complicated, plus theta. H3 is R sine theta, H1 is 1, so this is simply R sine theta, partial phi, partial F R minus partial R, partial F3, H3. Oh, right, 1. F phi R sine theta plus phi H1, H2 is 1 over R partial r partial f theta r minus partial theta partial f r. That's it. I guess you deserve maybe 5 minutes of break. So I will recording. So this we'll be studying divergence. So Q1, Q2, Q3 can be actually you can design whatever convenient for you. So let's consider some volume. So this is your surface 1, 2, 3, and 4, 5, and 6. And let's say center point is given by Q1, Q2, Q3. And the surface 1 is Q1, Q2, Q3 plus delta Q3 over 2. And the center is given by Q1, Q2, Q3 plus delta Q3 over 2. This is to be minus, I think. Sorry. Minus. And this is the direction of the surface, and this is the direction of the surface. So Q3 minus Q3. So on surface 6, let's do this integral f and ds. So on the 6th surface, the normal vector is in Q3 direction, right? So it's actually S3 here. So this is actually FQ3 TS3. And using mean value theorem, it can be expanded as FQ3 and multiplied by H1, H2, evaluated at Q1, Q2, Q3 over delta Q3 over 2, and delta Q1, delta Q2. And on surface 1, it's pointing minus Q3 direction here, right? With this coordinate system. So on surface 1, this integral f and dsn is actually minus fq3 ds3 is fq3 h1 h2 and evaluated q1 q2 q3 minus delta q3 over 2 delta Q1, delta Q2. So since we have some area, maybe I can write down here. So 1 plus 6 is what? That is FQ3, H1, H2, Q1, Q2, Q3 plus delta Q3 over 2 minus FQ1, Q3, H1, H2, Q1, Q2, Q3 minus delta Q3 over 2 times delta Q1, delta Q2, right? So what you can do is actually do nothing. Do nothing means you divide by delta Q3, right? H1, H2, H3, H1, H2, H3. Right? So then, can I move on to the next page, or maybe you still need time to copy? So I divide by this, multiply by this, and this becomes the part of the divergence formula for and next page. That's Q3, H1, H2, right? Is 3, 2 and 4, 3 and 5. So 1 plus 6. So surface 1 6 becomes this 1 over H1, H2, H3, partial Q3, partial QF Q3, H1, H2, H1, H2, H3, delta Q1, delta Q2, delta Q3, and this is actually the volume, delta V. So you can switch into this integral, H1, H2, H3, partial Q3, partial FQ3, H1, H2, dV. And you can do 4 other integrals, right? And I'm going to give it as a homework. So what are the 4? Do the other. We can do the other 4 integrals. And this is of course homework. Then we have the following. Including all these integrals gives the following. H1, H2, H3, partial Q1, partial FQ1, H2, H3, partial Q2, partial Q2 H3 H1 plus partial Q3 partial FQ3 H1 H2 dV. There's a divergence theorem in general coordinate system, and let me just check if my formula is correct. So H, and this is your divergence, right? Divergence of F. So Q1 H2 H3 Q2 Q2 H3 H1 Q3 Q3 H1 H3. I normally memorize everything, but sometimes I have to check. I'm getting old, so sometimes my memory fails. So I need this. This is my candle. The divergence is actually, I still need time to copy. So divergence is this. So divergence H1, H2, H3, partial Q1, partial FQ1, H2, H3, plus partial Q2, partial FQ2, H3, H1, plus partial Q3, partial FQ3, H1, H2. Correct? 3 by 2. So Cartesian coordinate. Cartesian coordinate. Q1 x, Q2 is y, Q3 is z, H1 is 1, H2 is 1, H3 is 1. So divergence of F is very simple, right? Simply partial x, partial fx, partial y, partial fy, partial z, partial fc. Cylindrical coordinate. Q1 is rho, Q2 is phi, Q3 is z, H1 is 1, H2 is rho, H3 is 1. So the divergence of F is simply H1, H2, H3 is 1, so simply rho, right? So 1 over rho, partial rho, partial F rho, because H2 is rho, partial phi, partial F phi is 1, and partial z, partial fz rho. Spherical coordinate. Q1 r, Q2 is theta, Q3 is phi, H1 is 1, H2 is r, H3 is r sine theta. So divergence of F is 1 to 3 is 1 over r squared sine theta. Partial r, partial fr. 2, 3 is r squared sine theta. Partial theta, partial f theta. H3, H1 is r sine theta. Partial phi, partial H1, H2 is f phi r. So if we are taking electromagnetic theory, then they will summarize your divergence curve and gradient. And one final quantity is Laplacian. It's a divergence of a gradient. So I will let you copy for that. So any questions so far? Can I move on? So gradient, we will remember Q1, H1 partial Q1 partial F, Q2, H2 partial Q2 partial F, Q3, H3 partial Q3 partial F. And divergence of F was, if you still remember, maybe I should start with the bracket. That is partial Q1 partial FQ1 H2 H3 partial Q2 partial FQ3 Q2 H3 H1 partial Q3 partial FQ3 H1 H2, right? That's your divergence expression for general coordinate. Let me just double check. H1 H2 1 1 1 1 1. So divergence of a gradient is called Laplacian. So in electromagnetic theory, you're going to learn Laplace's equation pretty soon. So sometimes it is written as Laplacian F. So you just substitute this H1, H2, H3 partial Q1 H1, H2, H3 partial Q1 partial F Q1 partial Q2 partial H2 H3 H1 partial Q2 partial F plus partial Q3 partial H3 H1 H2 partial Q3 partial F. That's your expression. So for Cartesian coordinate, everything's one, right? Very simple. So Laplacian F is simply partial x squared partial F partial y squared partial F partial z squared partial F. Very simple. On the other hand, cylindrical coordinate is very complicated. Cylinder. Can you see that? I guess. H1, H2, H3 is rho, right? So this is 1 over rho, partial rho, partial. H1 is simply 1, H2, H3 is rho, partial phi, H2 is rho, so 1 over rho, H1, H3, H1 is 1, partial phi, partial F, partial Z. H3 is 1, but H1, H2 is rho. So rho, partial Z, partial F. And spherical coordinate. H1, H2, H3 is r squared sine theta, right? So that is r squared sine theta, partial r partial. H2, H3 is r squared sine theta, partial r partial f, partial theta partial. H2 is r, H1 is 1, H3 is r sine theta. So r sine theta divided by r is just simply sine theta. Round phi, round r sine theta over r. So 1 over sine theta, partial phi, partial f. That's it. So we have expression for Laplacian. Let me check if it is correct. Sine theta phi 1 over H2. Okay, sine theta. Right. So any questions so far? Too easy? Too complicated? Just average? I'm going to stop here today, so I will let you have more time for the first quiz. So I'll be speaking here for maybe 5 more minutes. If you have any questions, don't hesitate to ask me. Was I going too fast? But you have a... Oh, let me stop.